Hello everyone, welcome to the last week of the Advanced Machine Learning course. Today's lecture is going to be about recurrent neural networks. So these are neural networks that are used to model recurrent signals, things that evolve in time, and they have relationships with previous observations or previous predictions. So in today's lecture, we're going to be looking into a few things. We're going to be looking into RNNs, LSTMs, which are two variants of it. We're going to be looking into medical applications, and we're also going to touch upon some new aspects around transformers. So what is the difference between a feed-forward neural network and a recurrent neural network? In a feed-forward neural network, as we've been seeing for a few lectures now, what you have is an input image or an input signal of some sort, and you then pass that through a function, which is approximated by a series of layers of a network, and you make a single prediction, or you make a prediction. It might be multiple predictions from the point of view, for example, multitask learning, but you make a set of predictions, a fixed set of predictions for a input that you give to the model. A recurrent neural network is a little bit different. A recurrent neural network is a network that is using previous observations as a way to make a prediction. So for example, if I give you a sequence of numbers, let's say 1, 2, 3, 4, the next step might be for you to predict that the number is 5, right? So I gave you 4 numbers and you're predicting that the next one is the number 5. So given 4 inputs, the network goes through them and says the next item is the number 5, for example. But if I now give you the sequence 1, 2, 3, 4, 5, 6, 7, the network now needs to predict that the next one is the number 8. And you just gave it 7 elements as an input. So from a recurrent neural network's point of view, the input is everything that has happened so far, regardless of how much was it. And the task is always to predict the next item or the next set of items. And it does so recurrently. So the function that predicts what the next item is always the same. For example, if you start with a number 1 and you want to predict 2, the function needs to add 1, for example. Obviously, if you now have 1, 2, then the function will now need to add 1 again to the last item. Right? So this is because the specific recurrent function is really short in terms of the relationship. But for example, you might now imagine a more complex series where it might be 1, 1, and then 2, and then 3, and then 5. So where you're adding, for example, the last couple of the digits of a sequence. And in that setting, obviously, the recurrent neural network will require to have a slightly bigger view. You can now imagine a more complex pattern where, for example, you might have long-term recurrences, or you might be modeling the signal of some system, and you always want to predict what the next sample is. So in a recurrent neural network setting, the temporal information, here temporal information is the variable that is describing the direction that we're traveling, right? So in this case, if it is a time sequence, for example, it will be time, it's temporal information. Same thing if it is, for example, speech or video, anything that is a sequence of events or a sequence of tokens or a sequence of things, then as you go forward in time, you have more tokens and you need to make a prediction. So what you see here is what I was trying to explain in the previous slide. You have a function here, let's call it function A. You give it an initial number, and you give it the function A, which is going to make a prediction. And that prediction is going to be this one. And then given that prediction and what the function has learned, you're now going to use that to make the next prediction. For example, imagine that you give the function x0, which is going to predict h0. And then whatever you've learned here is now enabling you to predict h1. So the prediction of h1 is not only dependent on x1, but is dependent on what was observed before, what happened before. So you can imagine that this is very important. Let's say x0, x1, x2 might be, for example, the different months of a year. And let's say you're trying to predict what is how much a store, for example, is selling of a specific product. Or in a medical setting, imagine that you're trying to predict how much of a specific drug is being used by patients, or how many patients come into the hospital with a specific type of disease. Obviously, if X2, for example, is the, let's say, January, February, March. So if X2 is the March month, what we're saying is our ability to predict how many, let's say, patients are using a specific drug in March is dependent, obviously, on the fact that we are in March, but is also dependent on what happened in January and February, because that year might be very special. For example, there might be a surge of a specific type of disease that might cause that specific drug to be used more often than it was in the past. So in a vanilla neural network, you basically have this setting where you have a one-to-one mapping. There's an input, which is mapped to one output. By one, I mean the output might have multiple dimensions, like for example in a multitask learning, but you're mapping it, you're making a prediction for each one of the inputs. While in recurrent neural networks, you actually have a much more complicated setting, where the number of inputs and the number of outputs might be one or many on both sides. For example, you might have a one-to-many problem. A one-to-many problem is, for example, if you have I'll give you, for example, the first few notes of a music and you want to predict the rest of the music. So that will be a one-to-many relationship. The many-to-one relationship might be, for example, the situation where I might show you many frames of a movie and you need to figure out what happened in that movie. Obviously, the movie might be a different length, so the size of the input might be more frames than others, but it allows you to collect information from multiple frames and make a single prediction from those multiple frames. It might be a many-to-many relationship. For example, this is the example that I was giving up here when we're saying, for example, different months of the year and maybe service usage as an input, and you want to predict how many drugs are going to be prescribed by clinicians of a specific department, or how many patients are going to come in with a specific type of disease. And you might also have a many-to-many relationship, but where the prediction is time delayed. For example, this is again an example here of speech or time series modeling, where rather than giving a single sample, you might give a series of samples, and you might now want to predict what's going to happen afterwards in the future. But the pattern here that we're inputting is a little bit more complicated than it was in, for example, this situation here. So the interesting thing about RNNs is that because we're passing functions through the same loop over and over and over and over again, if the sequence is very long, and because of the way that these are built, they tend to use these sigmoid activation functions and things like this. So the problem with sigmoid activation functions, or actually most activation functions, is that they tend to have vanishing gradients. What that means is, unless your activations are in a very specific range of the activation domain, the gradients tend to zero. So if your activations, for example, are, let's say, below 0.1 or above 0.9, so if you're somewhere in this part of the regime or that part of the regime over there, the size of the gradient starts getting quite small. And because your gradient is small, and because your activation is small, the gradient of the next layer tends to be even smaller, and then it gets smaller, and then it gets smaller, up until the point where the gradients themselves vanish. So it's incredibly hard to backpropagate through a recurrent neural network unless you design the neural network very carefully to make sure that these gradients do not disappear and do not vanish. There are two main problems that recurrent neural networks tend to face. The first part is because of their recurrent nature, because the same function is used over and over again on the sequence, the neural network needs to accumulate all of the information that has happened on that section, on that sequence, so that you're able to then make the prediction that you wanted to make from the beginning. So the network needs to memorize everything that happened. And because of that, unless the network has sufficient capacity, it becomes very hard for the network to memorize everything that has happened in a signal, because the signal itself might have been very long. Let's say you are trying to predict the next note in a music, and I've shown you the first 10 minutes of a very long piece of music, for example. Predicting the next note might be dependent on something you've seen in the past, maybe a few minutes ago. So that might mean thousands and thousands of samples ago. And that becomes quite hard for the network to forget old events and focus on recent things because of the way you backpropagate them. The other problem is the vanishing gradient problem that I was explaining in the previous slide, where if you apply many times the same network in a row, the gradients themselves go to zero, and you end up with a situation where you cannot really train all the way back to the beginning of the network. If you think about what an architecture of a recurrent neural network should look like, one part becomes very clear, is that we need to have a network that can choose to remember certain things and can also choose to forget other things. So how would that work in a neural network setting? So in a neural network setting, and there's a couple of symbols that you'll see there on the top left, but let's ignore those for a second. The simplest part that you can build on a neural network, on a recurrent neural network, I apologize, is to have something that would look something like this that you have here on the screen. You have a certain input xt, which is going to have a tensor product with whatever the network has, some parameters that the network has learned before. And these parameters here will then go through a 10H activation. So it's just going to be a value between 0 and 1. And that value there is what we're going to call our output. And obviously the same output, or the same thing that has been predicted before, is now going to be given to the next element of the network so that you can make the next prediction. This is very simple. It's not doing anything special. It's just basically combining information from the previous RNN with the current observation xt to be able to predict what ht is. So how do we now make this network choose what to forget and what to remember? So there's a few items here that we need to take into account. The first part is we need to understand the behavior of what the sigmoid activation function actually does. So a sigmoid activation function, for example here, is a function that given some number, some value before, is going to map that value into the domain of 0 and 1. So if you think about that 0-1 mapping being a gate, so something that allows you to multiply something by 0, which means you'll end up with 0, or multiply something by 1, which means you're letting it through, what this branch here is doing that selecting. It's saying, given what I've learned before, which is what's here, and what I'm observing now, can I put those two pieces of information together and decide on a vector, which is between 0 and 1, and depending on that vector being 0 and 1, I'm going to allow the same thing I've learned before and multiply by that. So the information here that is going to be flowing through this channel here is going to be dependent on the numbers that will come out of the sigmoid activation function. That's why you're multiplying them here. So this first part is purely defined as a memory selector, something that says I'm going to be using or I'm going to ignore the information that I've seen before. So the next step is really interesting. So what we have here, as per the previous slide, is information we decided to let through given this activation function. So this is the information that is relevant now. What we might also want to do, because we've removed some of this information by multiplying by 0, we might want to add information back. This is what's happening here in this plus. So this is adding information to the message that is arriving here. So which information can we add here in this location? There's two pieces of information that we want to go through. So we want to have a selector. So again, a sigmoid is always seen in an RNN setting as a selector, is letting something through or not. So the sigmoid here is deciding which values are going to pass through this arrow here, while the tanh is deciding what values are going to pass through that arrow there. So if you select what values you want to pass through this arrow here and which states do you want to update, you basically say, I want to update X states and you want these values to go through, which gives you this updated state here. And you're going to add to the value to the state that you had before. So you've deleted part of the state using the first part, and you've now added information to the state using the second part. So the information that you have now at this point is literally the state, is the current knowledge that the network has about your environment that is now conditioned on the new input. This is what you know about your system at the moment. So really these two top parts here perform the forgetting part and the state update part. So forgetting through the sigmoid and state update using the selector and the pass-through, which then give you here a state update. So this allows you to remove things from memory, and this allows you to add things to the memory. And the very last step of a LSTM network, also called a long short-term memory network, is to be able to perform the same thing we did before, but rather than being about updating the state, which is what we saw over here, what we're doing now is we're using information from the state, conditioned on a filter, on a selector given by the input, to be able to then pass the information to the next state, but also to make the final prediction. So we're taking the current knowledge of the world, select part of that knowledge of the world, and that is what's going to give us our output HD. And here we're going to pass forward a filtered version of the information that was here. So here at the top, we're passing the total information, while here below, we're passing the information that is relevant to be able to make this prediction. So there are two versions of the same information. The one at the top is a tanh transformed and filtered version of whatever was in this arrow here. So all of these systems together give you really interesting behavior when you can erase and add information to a system. You can then take your current view of the state of the world and perform a simple operation to it, which will then give you the new prediction. So if you put all of this together, you have what is called the forget gate, which is the first part of this module. You have the input gate, which selects which part of the information gets added to the state. You have the cell state, which is the top part. So this is the memory of the environment around you. And you have the output gate, which is something that selects part of the cell state and allows you to then make the prediction. This is the same output, which will also give you the prediction at the top in the previous slide. There's obviously other types of recurrent neural networks that are very popular. For example, another one that is called the GRU allows you to do something similar but different, and it has sometimes much better, sometimes much worse performance. So the GRU and LSTM are quite different, but they do things in a similar way. For example, the GRU uses this called the reset gate, which is a way for you to use the input information to know what to delete and to reset parts of the state. So it allows you to completely null the state if needed. The update gate on this side uses a trick that I actually find really interesting. So whatever the selector here is selecting is going to be multiplied here and is going to basically allow you to add this information to the current state. So this selector is going to select which information gets added. But the same selector gets multiplied by -1, which will then allow you to multiply here and allows you to remove things. So the same selector removes some information and adds other information in that location. So this is basically saying this update gate is called an update gate because it's removing and adding in the same location as defined by the selector. So it gives you a parametrically more compact version of an RNN, which obviously in many settings can perform better because of that parametric compactness, but in some other settings might not perform as well. The other interesting part when we're looking into LSTMs is to think about what backpropagation looks like. So backpropagation in an LSTM setting is the same thing as in any other neural networks. It's just that we need to perform that backpropagation through every single one of the networks in a recurrent way. And because they're recurrent, you need to be able to unwind all of your networks, all of your forward passes to be able to backpropagate through your network. So for each one of the RNNs, you have a gradient coming from the prediction. You have a gradient coming from the cell module in front of it. So from the prediction here, from the cell module in front of it. And that back propagates all the way to the input. Obviously, you're not changing the input, but it does back propagate all the way back. And you see that the gradients flow in a relatively complex way. And they can flow through many, many, many different items until you, for example, go all the way to S0. So each one of these blocks, each one of these S's is comprised by, for example, in this case, an LSTM. And because it's comprised by LSTM, the gradients for each one of the items looks like this. So the gradients for the state part, for the A part, the I part, the F part. So all of them are defined here for each one of the items that you see here with these definitions here that you have there on the left. So obviously you're not going to calculate this by hand in your own neural network implementations. This is all given to you by your auto-differentiation tool that you might use. But obviously, this is what's happening inside. So a module like this actually has a complex series of gradients that are estimated like this. And when you estimate those gradients, then you can estimate the gradients of the one before and the one before through the standard backpropagation process. So one of the issues that exist is when we have long-range interactions and sequential processing, when you mix those two at the same time. So LSTMs, as you've seen, have these two components. Have the component that comes from the new input, which allows you to select which information you might want to keep or to throw away. And you have the current state, which is at the top, which allows you to keep some information, to memorize things from the past. So even with the help of these gates, you still have this limiting performance that it comes from the fact that you need to be able to memorize things that might exist in old entities. And also, if the amount of memory you have, if the state size is not big enough, you will need to decide to delete certain things to then be able to add new things to it, because obviously your memory is limited. So your amount of memory is limited also. And the reason for it is because the network notices from the very beginning that the probability of a sample that has been seen many, many, many items before to influence the next sample is much less than, for example, the sample before. So the immediate past is a much better prediction of the immediate future than maybe something that has happened 100 cells before or 100 items before. On top of that, the input also needs to be processed sequentially, one after the other. This is a recurrent neural network after all. And because of that, the recurrent neural networks do not really make optimal use of GPUs because they are sequential. You apply one RNN after the next RNN after the next RNN. It's not very easy to parallelize this. And because it's not easy to parallelize, graphic processing units often do not speed up RNNs that much. Obviously, they still do, but not as much as one might want. Another way that is really interesting to think about LSTMs, so the idea of LSTMs is that if you have a sequence, for example, a sequence of tokens, or a sequence of time events, for example, or a sequence of observations, you're using the memory or the state representation of a neural network to be able to memorize what has happened in the past so that you can make use of that information for the next prediction. And if you think about it, what all of those systems are doing is they are selecting parts of the information using the selector and the forget and the update part of your LSTM to be able to define what the LSTM should ignore and what the LSTM should preserve and should use. And if you think about it, that's actually surprisingly similar to some things that we've seen in the past. For example, if you look at the concept of attention, the concept of attention, or in this case, the concept of self-attention, is actually doing something that I wouldn't say similar, but that is trying to achieve the same end goal. So self-attention is a mechanism where the neural network draws and learns to draw attention, to look into the dependencies between inputs and outputs, And self-attention allows you to choose which inputs should you interact with to be able to find how they are related to the output that you want to make. For example, if you have a sentence here, let's say you have the sentence here, the animal didn't cross the street because it was too tired. And it's written in a funny way, but that's because it's the way that that has been tokenized. If you want to, for example, predict the word it, so the animal didn't want to cross the street because it, and obviously the word it is there because it is an animal, right? If you try to find out which information of the sentence predicts that this word here should be it and not, for example, he or she, the model can say, actually, this prediction it, I should attend to these words here. For example, the animal didn't. All of these things will influence the fact that this word here is it. So self-attention also allows you to select which one of the past observations are going to influence the decision-making of that token being there, for example, or that one being the correct next token. So it aggregates information and the interactions between this information using this attention mechanism to be able to allow you to make a better prediction. So how does self-attention actually work? So self-attention, as the name says, is a mechanism where, given a series of inputs, you want to be able to learn to attend to different inputs to be able to make a prediction. Let's say your inputs are just words in a sentence, one after the other, or they might just be items in a sequence. It doesn't really matter. So you have input 1, you have input 2, and you have input 3. So those are 3 input sequences that you might have. So what self-attention does is it calculates basically this equation that you see here at the top. You have these QK transpose normalized by the square root of D, multiplied then by V. So V is the value, K is the key, and Q is called the query. So these things together, and with that normalization term, are passed through a softmax and then multiplied by V, and that gives you your attention mechanism. Okay, so what does this attention mechanism actually look like? So given a specific input, what we do is we're trying to predict what the key value here looks like. So the key value here is then combined with the query. So we're combining this one. You're doing a vector-vector multiplication between this and this, so that it gives you your score, which is what you're seeing here. So after we do a vector-vector multiplication between the query and the key, we get the score, and the score is then multiplied by the value to give us this multiplied value, right? So this is the value that is going to come out. Also note that this score here needs to be normalized. So the sum of the scores over all the elements of the sequence, so the sum of that score plus that score plus that score, needs to sum to 1. That's what this normalization bit here is doing. So we do a vector-vector multiplication, we calculate an intermediary score, and then we renormalize them. And because we renormalize them, you can think about these as a form of selector, right? We're saying we're giving more emphasis to that part than to that part, because they have the value 0.5. And we're giving 0 influence to that part. So this score here is your attention score, right? This is the part that you're getting here. And this attention score is then multiplied by this value here. So you multiply 280 by 0.5, so you end up with 140. And then you have 263 multiplied by 0.5, so you have 1.5. And here you have 0 because you're multiplying by a score of 0. And now you're going to add the different numbers that you have here at the top, which is going to give you your addition, which is 2, 7, 1.5. So this is the prediction that we're getting out of the self-attention part of the network. So in these transformer networks, which make use of the self-attention, they basically use the attention mechanism you've seen in the previous slide. They are these multi-head attentions that you're seeing here. And they combine these with feed-forward layers and with positional encodings to be able to create these networks that can model sequences incredibly effectively and with a long ability to have, for example, very long distance relationships in the data that enable you to make better predictions of future events or future tokens. So transformers really rely on attention mechanisms to be able to capture the interactions between all the different inputs. And they were proposed for many things, primarily to do sequence-to-sequence modeling, for example, doing many-to-many token mapping. For example, what you see in text translation, where you're translating, for example, from English to, I don't know, Chinese, for example. And it was originally achieved with an encoder-decoder architecture. But the key insight here is the use of self-attention, is the idea that self-attention is actually all that you need. And the original paper was called Attention is All You Need, which was kind of a cheeky title. But attention is all that you need to be able to use past information and to attend to past information to be able to make the next best prediction. Okay, so we've seen now different types of recurrent neural networks, all the way from LSTMs, GRUs, but also transformers, which are based on self-attention. Now we're going to look at some applications of these networks in a medical setting. One thing that has been done with these networks is to use them for segmentation purposes. For example, in this specific network here, they're breaking the image down into three-dimensional patches, and each one of these patches are embedded and passed through a LSTM or a RNN type network. And this RNN type network aggregates information from all of the patches at the same time until it predicts the location of the patch that has the object of interest. And by doing that, allows you to then have a segmentation component which only works on that specific subpart of the image which contains the object of interest. So for example, you see here an example on the right, where you have the images at the top and you have the segmentations that the proposed method would do if you were to use these LSTMs, or if you're trying to, for example, just use a standard unit. So the interesting thing about this method is that it can actually write and understand specific geometrical constraints, for example, the presence of folded cortices, or the fact that certain organs have a very specific shape, because it learns the spatial relationships between these tokens, maybe more accurately or more precisely than if you have, for example, a unit. So in the same way that the previous paper that was shown in the previous slide was using a transformer, the interesting thing about transformers is that they can model any sequence of tokens. So there was a paper that was published very recently, actually by a postdoc in our group, that was using transformers to detect anomalies in images. So what's interesting about this concept is that if you have a way to encode an image into a series of tokens, which you can achieve, for example, using vector quantized VAEs, which we've learned about in a previous lecture. So the vector quantized VAEs gives you a series of quantized vectors, so a series of categorical numbers, which you can think about as tokens. So if you embed a series of healthy subjects and learn the token distribution, the quantized numbers of healthy brains, if you now give this network an unhealthy brain, you can figure out that certain of these tokens shouldn't be where they are. And that's because that sequence that shows that, for example, there's a lesion in a specific part of the brain has never been seen before in a healthy population. So what you can do is you can find areas that have a low likelihood, so where they shouldn't be there, and replace them with an observation that would increase the likelihood, increase the likelihood of that observation, meaning that it will make the brain look a little bit more normal. So by doing this, what you can do is you can replace the bits of the brain in an image that are pathological with the equivalent anatomy that you would have seen in a healthy subject. So you are removing the pathology from pathological subjects and turning them into healthy again. If you now have a healthy version of the input image and you compare it to the input image itself and you subtract the two, what you see is basically what you see here. So you see the blobs that are highlighting this our method is nothing more than the subtraction. He also has this masking scheme, which if you can read a little bit more about it if you look into the paper. But this is basically the subtraction between the prediction and the input image. And you see that the subtracted areas, the areas where there's any signal, are areas that contain pathology. And it's also something that works very well in many different modalities. You see, it has never been trained on this modality, but it works well on the Slovenian dataset for MS lesions, the BRATS dataset for brain tumors, and also on the white matter hyperintensity challenge data, even though he has never seen that data before. And I think what's quite impressive here is that these segmentations here are done in a almost unsupervised way. The only form of supervision that the network received was the fact that it knows which images are healthy and which images are unhealthy. So it's using the knowledge of healthiness to be able to define what healthy brains look like. So pathology is here defined as any deviation from normality. So you can, for example, take these as areas that appear to be pathological. Okay, so with this in mind, let's actually now go back to the Jupyter notebook, if you have the time. Otherwise, we'll do it during the tutorial session. And let's implement an LSTM from scratch and apply it to a time series. We chose here an LSTM because it's really the foundation of what recurrent neural networks look like. And I believe that implementing one of these from absolute scratch is pretty essential for you to understand exactly how they work. So if you have a time series, let's say you're looking at something which obviously everyone would like to solve. Let's say you're looking into the stock market. And I know this is not the objective of today's lecture, but let's just imagine this for a second. Let's say this is what has happened to IBM, the IBM stock. And so IBM went up, it came down a little bit, and then it went up again. For many reasons, it doesn't really matter. So what if you are to train a recurrent neural network? So imagine this as a sequence, right? There's a sequence of events happening here. And you get to a point where you stop and you say, what if this was my training data? This is all that I've seen before. Can I predict what's happening next? Because if you can, you're going to be very rich. So the signal here is quite interesting. And there's a few interesting bits that we should look at. So there's a lot of stochasticity and randomness. There's things that are timed. So for example, at certain time events, you have these events that bring the stock down or the stock up. But there's also a lot of wobbliness, which appears to be fluctuating and to be recurrent. So if you ask the model to be able to, for example, given some data, be able to make the predictions during the training set itself, the predictions might look, for example, like this in orange here, where, or actually the blue line below, where the predictions match exactly what the data looks like. So if you were to train on this part of the data, on the training set, your predictions basically match your data really, really well. And then what you want to do is to say, okay, this is what I know about my network. This is what I observed until now, right? This is my state. Can you now predict what the next item is, and the next item is, and the next item is? And you would hope that your predictions look exactly like the data here, even though the network has never seen these, right? So if you can show that that's the case, obviously this will be retrospective data. The idea will be to then apply this to prospective data and show that this basically can learn how this stock will vary. Obviously, this doesn't work as well as you'd expect in this specific setting because the stock market is incredibly chaotic and it has a couple of other sources of randomness, let's say. So this is not one area where algorithms, LSTMs more specifically, have made a big change. I mean, don't get me wrong, they are used. But they don't have an amazing result. So no one managed to get absolutely gobsmacking rich just by doing this. A much more interesting question would be to say, okay, how can we apply this to other applications that might be a little bit more interesting? When we are training these neural networks, we have a series of steps that we need to do to be able to make these predictions. For example, in this specific setting, we want to have a network that, given a video stream, is able to then generate a sentence or a caption describing what was happening in the video. So we're showing the video to the network, we're giving it to this red LSTM, and then it gets to a point where the video finishes, and we now want to predict this word, the sentence here saying, a man is talking blah, blah, blah on the phone, for example. And what's interesting is these are two separate LSTMs, and the LSTM obviously is given an input when the video is here. And after this LSTM has finished receiving the video, its state, the hidden state of this LSTM is complete. And now we have the inputs to this LSTM as being an empty vector. So we're just giving it empty frames from now on, which means your LSTM is going to basically preserve its current state. And the LSTM state is going to continue being exactly the same from this point onwards. For the green LSTM, is the other way around. So the green LSTM starts with padded values, so with 0 values. So the LSTM has no information whatsoever here. And it gets to a point where we cross this last frame. So the LSTM basically gets kickstarted. There's this message here that arrives that says start your LSTM. And now your LSTM is predicting the letter A. The letter A is going to go there, and jointly with the state of the world is going to go to LSTM, predict the word man, and etc. So by recurrently decoding from the system, you can then write a sentence which was the content of the video that was being played. And there are a couple of examples of this working. Obviously, LSTMs are not the easiest thing to train, and they're not the most stable type of networks, but it has been shown that it is possible to absorb knowledge from a video and then write text about it. So the network has shown that it can summarize the information from the video within the states of the LSTM itself. Maybe a much more interesting application of this is the detection of abnormal EEG using these kind of methodologies. So if you were a scientist, for example, or if you're a scientist and you want to acquire EEG data from patients, you need an incredibly highly trained clinician to be able to look at all of these traces and understand that, for example, these things here might not matter at all, but these ones here look very important and matter quite a bit. And in this specific image, this looks pretty obvious, but there are many situations where even I've been looking at this for a bit and I cannot see them, while epilepsy clinicians will very, very clearly see the patterns there. The idea will be to say, can we ask a RNN to assist one of the first steps in interpreting the EEG session, which is to identify if the brain activity is normal or abnormal, right? This will be a really interesting example of the use of this kind of technology, and it has been proposed in this paper by Roy et al. That you see above. More specifically, this paper uses a series of convolutional neural networks, one-dimensional convolutional neural networks, to be able to feed the features into GRU layers. And these features are then combined into another GRU, into another GRU, into another GRU, until you basically get a good model of what the EEG signal looks like. So these 1D convolutional layers that are using these conv1Ds that you see here, they use multiple filters of exponentially varying lengths. So this is what you're seeing here. So this allows the network to create feature representations that have a multi-length view that can see further out than others. And then you basically stack these GRU layers in a way that they're densely connected to each other. You see this part here, they are densely connected. So there are shortcuts between different GRUs so that you're allowing the gradients to flow through it a little bit better. And this allows you to then model the data really well. So again, if you train these models only with healthy data, you can then basically find these deviations, and allows you to detect these abnormal versus normal data in 86% of the time, which is actually quite good for a machine. Another item, which this is where RNNs have been used, is to track physical robustness of healthcare in patients. What this means is if you're a patient, for example, What you can do is you can give them a body sensor, for example, a ECG scanner or a accelerometer or a magnetometer, even, for example, an Apple Watch, which you might have on your wrist. And you can then use the information on those devices to try to predict something that has been happening to the patient without the patient having to report things themselves. So using wearables, for example, to recognize certain types of behaviors so that you can, for example, assist in the rehabilitation of these patients or improve the way that they are treated in their care. So let's imagine that you want to figure out if someone, for example, is, let's say, is obese or had a stroke or had, for example, epilepsy. You might want to figure out, are they standing still? Are they holding their balance? They climb stairs? Are they exercising or jogging or not? If a patient, for example, has a seizure, can you detect that seizure or not? Because patients do not remember the fact that they're having seizures. All of this information is incredibly complex. And you can imagine that in this paper here, what they did was they took the time series that was coming from all of these different devices to be able to make these predictions. And these predictions can then be used clinically to inform, for example, the status of a patient and to call the patient back for a secondary assessment, for a new drug treatment or a new intervention that might help them save their lives. Another item where RNNs can be used is on something called the disease progression model. So disease progression model, as the name says, is a model that tries to predict what the next step of the disease progression should be. So in this specific example that you have here in the image in the middle, the model predicts a sequence of events that happens to people's brains, in this case, patients with Alzheimer's disease, that tells you what is your state and what is the next step that you would expect in terms of your deterioration if you have this condition. For example, it tells you, and it discovers this automatically from data. This is not human prescribed. This is something that the model has learned by itself. That, for example, the ventricles and the hippocampus are affected first, then the whole brain starts to shrink, and then the fusiform, and then the middle temporal gyrus, and then the entorhinal cortex are the areas that start getting affected by Alzheimer's disease. And they have a specific sequence and a specific order. And depending on the sequence and order, you might have a better or a worse prospect of how this disease is going to evolve. So in this specific setting, everything is based on medical images, but obviously the same exact things can be applied to non-imaging data. For example, you could be looking at the different types of medications that the patients are taking. You could be looking at different types of treatments that they might have received. And by using all of this information jointly, the objective might always be, okay, what is the next step? What is going to happen next? Can we now understand, for example, that all this data has been observed so far, and what we want to figure out is what the next blood sample, for example, is going to look like. What is going to be the next event? So it becomes a really interesting process to think about. And because it's a recurrent model, it doesn't require all the information to be available. It doesn't require the length of the sequence to be the same. It's just you feed the data to the model, and the model learns to use that data in the best way possible to create its internal representation so that they can make better predictions. This slide is only showing you here what an LSTM unit will look like for this kind of setting. It's similar to what you've seen before with a couple of small modifications, which we're not going to go through at the moment. But when you put all of this together and you use these LSTM models to be able to predict, for example, what is the next best, what is the next area to be affected, or what's going to be the volume, for example, of a region of the brain in the next few months, for example, or years, you see basically that LSTM methods can significantly outperform regression-based methods, as you can see in some of these scores here below. And also that they tend to be more robust to missing data. For example, here on the x-axis is the amount of missing data, and on the y-axis is the average test validation across the different MRI biomarkers. And you see the LSTM robust method achieves a much better performance or a much smaller error for most of the domain. until you cross more than 77% of missing data. So it's incredibly robust to missing data and much, much more accurate until the very end when you're reaching the top amount of missing data that you might have in a system like this. Another really interesting model where LSTMs have been used, again in imaging data, has been to use the text that describes, for example, an exam of a patient to be able to improve the way we can classify and diagnose these patients. For example, we might want to use the patient history or some clinical details, the fact that they are a male of a specific age, that they are of a specific height, maybe BMI, any kind of clinical information that might be of relevance about the patient. This information here is fed into a neural network, and this neural network allows you to then say, okay, given this information that I've seen so far, this is the part of the brain that you should be looking at. The information, a little cube is extracted about that part of the brain. The cube looks like this. And there's a glimpse that is taken from this cube. And depending on the information that is taken from this cube, it feeds again into the recurrent neural network, which gives you a new location that you need to look into. And this new location gives you a new glimpse, and the new glimpse gives you a new recurrent neural network update, which gives you a new glimpse, and you keep going through this. And if you think about it, this is kind of what a radiologist does when they look at data. They look at the patient clinical history, and then because of that, they already start looking at specific parts of the brain which they know they're going to be interested about. And depending on what they see, which is what the glimpse network is doing, they decide where to look at next. So this allows the model to basically look into different parts of the brain and follow specific paths that are of relevance depending on what they've seen so far. And at the end of everything, what you end up with is to say, okay, given the current state of the world, can you now give me a classification network? Can you now classify what the output is? And if you think about it, that's again what the clinician does. They collect information as they're reading the scan. And when they conclude the reading of the scan, they basically just give you what the diagnosis is. They write it down in the form of a report. And because the objective of this approach is to maximize the expected reward that the agent, in this case the LSTM or the recurrent neural network, receives by traversing an image, what you're actually doing is you're using the classification and the glimpse network are being optimized for cross entropy, because obviously you want the classification to be correct, and you want the glimpse network to also glimpse at the right parts of the image, which are of relevance. And the location and the context that is extracted are updated and optimized by the total reward. So you do not care about the reward for each one of the individual elements, but you care about the reward in the end after you go through all of the elements. So obviously the locations might be heterogeneous, but you would want the network to go through all relevant locations to be able to collect all the information that it needs to finally make a prediction, a classification at the end. Here you have some examples of what it looks like. For example, some of the paths that are taken by the network. A network might start in that location and then look at the cerebellum and then start going up and look at the occipital part of the brain in this specific subject. But in another subject, the path might be completely different. For example, it might again start in the middle of the brain, then go all the way to the back, then go to the cerebellum and then start going up. And in another situation, they might use some other path like this. So it's really interesting to see that they tend to start always from the same location. They probably get some initial information about what the patient looks like by looking at that part of the brain. And then they decide to either go down immediately, to go to the back of the brain and then go down. So the algorithm makes different decisions to be able to collect this information. The other interesting part is if you just compare it with the CNN that is trying to just classify the data, nothing else, you see that the balance accuracy of a CNN is 87.5, while the balance accuracy of this method here was 98.5, which obviously is quite high, but more importantly is a model that is slightly faster and has a specificity which is, in this case, of 100%, which is quite incredible. So if we look now into the world of image segmentation, we've seen already one or two examples there, but there's actually more that we can look at. So if you think about the use of CNNs in 3D, applied to image segmentation, you normally require a few things. You require the image itself to be of a constant size. That's because the network that you're training is going to receive a patch, and this patch is going to have a specific size, which you're then going to give your network a specific tensor so that you can make the prediction. And if this tensor is changing at every fourth pass, that can cause quite a few problems unless you're really good at the engineering side of the network. Because of the size of this patch and because you need to receive the full patch at once, it needs to actually have quite a strong memory capability, right? So the network has quite a few parameters and you need a lot of GPU RAM to be able to feed a large patch. And you need to feed a large patch because the network many times need to see far enough away to be able to make a decision for the label of a specific pixel. And also, all the slices of volumes have to be available at any given time of the test, of both of testing or training time. What this means is that you obviously need to have all the information available for you to be able to train the model, and also for you to be able to test, because you might want to use, for example, information from all the sites at the same time. So there was this paper here which proposes to address these problems that are described above, that normally exist, for example, with UNet architectures, by using something called a bidirectional convolutional long short-term memory network, or CLSTM. So what they do is they feed these images to a bidirectional CLSTM network, and this allows them, by the use of these contraction and expansion blocks, to comprehend the data and to make use of this data in an efficient way that allows them, for example, to have a much smaller requirement in terms of memory, and also the data does not always need to be resampled to the same scheme, because the network itself is using a neighborhood connectivity and memory as a way to preserve information from the full image. And they were able to show that segmentation can actually be quite competitive using this model. Yes, we all know that segmentation is evolving very fast, and all of these results might be valid today and maybe not tomorrow. But it's interesting to see that the method based on a sequence, and you can imagine that an image is a very complex way of modeling a sequence, because the easiest way for you to think about an image as a sequence is to just linearize the image, which will give you a very long vector, but you then lose some of these spatial relationships between them. And even then, the network was able to memorize and to segment the organs that were targeted pretty well. So just to finish up and to show you how interesting the potential of these networks can be, there's this very recent paper from this year that they were showing that you can integrate information coming from multiple sources to be able to better understand the brain functioning and predict clinical scores and other different types of clinical variables. So in this specific setting, what we see is this method that takes diffusion tensor imaging, which gives you something about the structure of the connectivity of the brain, and resting state fMRI, which gives you a temporally dynamic pattern of connectivity. And we combine these two. So we use the structural part to regularize the functional part. So we're saying that functional activation should only be activated when there is when it fulfills the criteria that we're observing from the structural data. Then this information is then embedded, and we create these temporal models, these temporal embeddings. And these temporal embeddings have a time varying component. So at each second or each millisecond of observation, we're getting a different temporal embedding. And we're feeding these temporal embeddings to an LSTM, which is making sense out of them, is creating a worldview of what's happening in the person's brain. Obviously, it's not about the thoughts, but it's just understanding the functional patterns that is observing. And these functional patterns at the ends of the sequence can then predict, for example, a multidimensional clinical severity score or some clinical variable of interest. You might predict that the patient might have schizophrenia of a specific type or something like this. It also allows you to understand, for example, specific brain networks and brain connectivity patterns that might be clinically relevant. Okay, so just to finish up, so today we've learned about recurrent neural networks and what they are, and you really should take some time to understand properly how the LSTM network works because of how popular it is And the fact that is one of the most elegant neural architectures that exist in the many, many years in the past. The other thing that you should probably focus on today is really understanding transformers. They went from a paper a few years back called Attention is All You Need to basically taking over many, many different applications, including medical image segmentation and classification. Transformers are now being used for many different tasks and they have incredible performance. So you should really understand how they work so that you can apply them to your own research and your own future work. You also understand, hopefully by the end of this lecture, how they actually work. So you have some insights about their inner workings and the different types of gates, and also on the attention part, how attention actually works and how it focuses on specific components of a sequence or specific components of a signal. Lastly, even though GRUs and LSTMs and transformers have been initially applied for sequences and tokens, you can see that they have many applications in the medical imaging scenario. You see applications in classification, but also, for example, understanding the context and the content of different types of functional images. But you can also imagine that anything that has to do with creating time series is important for biomarker discovery and for predicting the future of certain biomarkers, predicting the next few steps that the patient might go through. For example, if the patient is going to improve or deteriorate further. But it's also very important as a way and as a tool to be able to do natural language understanding. We haven't really discussed much about natural language in this course, but the important part here to take home is that in the medical setting, a lot of the communication that happens between clinicians is via language. So actually, if that language can be understood by a computer, which can now be done pretty accurately with the use of transformers, then this information can be used to either train neural networks or just to inform the rest of the remaining part of the clinical workflow. So you can imagine that transformers and sequence models have quite a lot of utility and are here to stay. With this in mind, I hope you enjoyed today's lecture. And if you have any questions, as always, either email me or post a question on Keats, and I'll be more than delighted to answer those. Thank you very much.